Welcome everybody. Today we'll be discussing the use of the Phi matrix in differential equations. This is a really important matrix. Right here is our Phi matrix. This matrix really will help us to solve these differential equations in this form. X prime is equal to a times x. X prime and x being vectors, a of x being a matrix. And so our a of x matrix, we will consider it to be a 2 by 2 matrix. This 2 by 2 matrix then will have the vector x prime and x in this form. Similarly, we will be solving for x, which will give us the solution to our differential equation. This gives us two equations, x of t and y of t. These equations, they're really going to help us to solve these differential equations. The Phi matrix is very helpful. The general form of the Phi matrix is given here. It is given in eigenvector value x1 e to the eigenvalue 1 times t. And then, as you can see, eigenvector value 1y e to the eigenvalue 1 times t. And the same thing for the right side there. For the sake of time, we will be given our eigenvalues and our eigenvectors. If you need to review them, please do so. These eigenvectors and eigenvalues come from our matrix A over here. So let's go ahead and get started. Just to be clear, this is a homogeneous differential equation. That is why we've been given some initial conditions to help us solve for our x of t and our y of t. So to generate our Phi matrix, we're going to substitute our values into the general form. This is going to look like 3 e to the 3t 2 e to the 3t 2 e to the 2t and e to the 2t. Okay, so like I said, our 3 is going to correspond here. Our 2 of our eigenvectors is going to correspond here with our 3 eigenvalue corresponding to our eigenvalue there. So this is our Phi matrix. That's it. This Phi matrix is really helpful, and so we're going to use this now to solve for a homogeneous differential equation. So to solve for a homogeneous differential equation, we need to get our constants, so C1, C2. So when we multiply our C1 and our C2 to our matrix, we're multiplying a 2 by 2 matrix by a 2 by 1 matrix. Make sure this is really key, because here initially it can kind of get a little bit crowded in here in our matrix. It looks sometimes like a 2 by 1, but we're multiplying a 2 by 2 by a 2 by 1 to create a 2 by 1 matrix. So we're going to get a 3c1 e to the 3t plus a 2c2 e to the 2t. Remember, just one column. Okay, so then we get 2c1 e to the 3t plus C2 e to the 2t. So now we have our Phi matrix. We can now use our initial conditions to generate two equations and solve for C1 and C2. So we use right here our x of 0. We're going to plug in 0 in for t into our x equation. This right here, our first row is our x equation, our second row is our y equation. So we're going to substitute in 0 in for t and solve for C1 and C2. So we're going to get 3c1 plus 2c2, because as we substitute 0 for t, our e term just goes to 1, is equal to 2. Then I get 2c1 plus c2 is equal to 3. Now, in these equations you can solve it any way you'd like. I prefer elimination. You can also use substitution, but to solve for these ones you will find that c1 is equal to 4 and c2 is equal to -5. So to finalize our homogeneous differential equation solution, we will substitute in 4 in for c1 and 5 in for c2, making sure to multiply by the constant out in front of them. So for our c1 and our x equation, we'll get 4 times 3, so we're going to get 12 e to the 3t, and then we're going to get -5 times 2, which is going to give us -10 In our y equation, we're going to get 2 times a 4, which is going to be 8, e to the 3t, and it looks like minus 5, e to the 2t. So we have now generated our equations. Limiting our constants, we will get x of t is equal to 12 e to the 3t minus 10 e to the 2t. And our y of t equation is equal to 8 e to the 3t minus 5 e to the 2t. And that will be the solution to our differential equation. Alright, good luck.